Today I will talk about in-sensor computing as one of the interesting hot topics where DALP can really be used. And I will first start with in-memory computing because this is where the in-sensor computing kind of is related to. And in-memory computing is basically AI. So as you know, today is a big hype about AI. Everybody wants to do AI. We have Jacques, AI expert, coming to the room. And basically AI is based on artificial neural networks. These are these days mostly run on software. And people realized very early on that to really get the efficiency where it should be, we have to make these in hardware. And the basic operation in a hardware neural network is VMM, vector matrix multiplication. And people realized like the ultimate scaling of hardware neural network can be implemented using simple devices called memristors, which is basically a capacitor structure where the dielectric can be electrically switched to have different resistance. So basically it's a programmable resistor, called memristor. And people realized that by creating this crossbar array on the bottom right, a crossbar array of these memristors, you can create one such layer of neural network. Basically, you can program every memristor to different state, and that give you your weight matrix. And then on the input, you have different voltages. That's your input voltage vector, gets multiplied by the weight matrix of resistances. And then the output, you immediately get the currents, which represents the output. So this is the core idea of using memristors for in-memory computing. And one step from this is in-sensor computing. So in-sensor computing, basically we, instead of just programmable memristor, we are using sensor. So on each node, there is one sensor, and this sensor is sensitive to some outside variable, let's say temperature or gas concentration. And this is not interesting if all the sensors are the same. But if you can program every sensor, either as a memristive sensor, which usually doesn't work very well, or if you can program every sensor in a hardware way to have different sensitivity function, then basically you get the outputs which gives you what you want. So basically you have input vector of voltages, you have programmed sensitivities, and output gives you basically direct output based on the sense variable. So as you see the sense variable on the bottom, if it's in the low numbers, let's say the first output is the winning one, and as you increase the temperature or gas or whatever sensors, you have different outputs winning. So this is a simple single layer neural network which is basically doing classification of the outside variable. And for making this, you need several different things. So first thing, you need a sensor which is compatible for crossbar implementation. That means you need sufficient device nonlinearity, otherwise the current will just flow through the path of least resistance. That's not going to work. So your sensor is ideally a diode or some sort of highly nonlinear element. Then you need a technology to engineer the sensitivity function in hardware by either changing the lateral dimensions of the device, for example using maskless or e-beam lithography, or the device thickness, so meet DALP. And then you need a simulation to kind of estimate where to deposit what kind of thickness to get the desired function. So in this example, we are using a titanium oxide-based hydrogen sensor. This is a very simple structure, MIM structure with titanium nitride bottom electrode made by PVD, titanium oxide film made either by ALD in our lab or DALP in this lab right over here, and platinum top electrode, also PVD. So in titanium oxide, there are two different gas sensing mechanisms. One is basically desorption of oxygen from the grain boundaries. This was well described already. And another mechanism is the Schottky diode barrier modulation, which I have on this slide on the right, but let's go a little bit back. So why are we using ALD for titanium oxide? Because ALD, I don't have to explain it here, it's reproducible, it's lab to fab transferable, and basically the DALP is also ALD, so that's why. And also we get crystalline layers without any further temperature processing. You can see the titanium oxide, on the top, the plane top view is on the right. You can see it's very nice granular structure. So if we deposit this kind of device with titanium oxide film in the middle, and when we introduce hydrogen, this modulates the top Schottky barrier between platinum and titanium oxide. And you can see how these diode characteristics dramatically change, even at room temperature, as a reaction to different hydrogen content. So if you see the IV characteristics in the middle, the black curve is without any hydrogen. You see this is a very good diode, a negative bias bias is very low, positive bias is super high. And if you increase hydrogen concentrations, you get orders of magnitude difference. Now the question is if we can tune this sensor by changing the thickness. So we found out the question is yes. By changing thickness with ALD, it's super easy. So from 15, 20, 30 nanometers of titanium oxide, you have these different responses in these small sensing voltages. So that's first good thing that it works. So basically now we're going to how to engineer these sensors using DALP. So this is the first test wafer deposited by DALP for the platinum vertical bottom electrodes. Then there is this square that's the titanium oxide. From top to bottom you have a thickness gradient from like 40 nanometers down to 5, and then the horizontal lines is platinum again. We did some analysis using Raman, so you can see the intensity of the Raman peak, which corresponds to anatase titanium oxide. You can see how it's nicely scales with the thickness. So this is how the test sensors looks like. So these are simple crossbar structures where you have this green stripe that's again titanium oxide of different thickness deposited here by DALP, and then we measured the response of these DALP sensors. So this is for different thickness, again 20, 30, 50 nanometer. This is the IV curve on the positive side. So again you can see it nicely scales with the hydrogen concentration. What is important, the dynamic response, that means how fast your sensor reacts to the hydrogen, is also changing with the thickness. And this is something which was exploited in our work. So this is something we are exploiting in the project we have with ATLANT, funded by Emeranet. This is a 3-year project. Now we are in the 3rd year. We are the coordinator responsible for device fabrication and characterization. We have a sister university for the hydrogen measurements, also in Bratislava, ATLANT, and National Yangming Chiao Tong University from Taiwan, who are experts in this neural network design. And I'm proud to announce that the first output of this project will be presented at IDM next month in San Francisco. It was accepted to sensor division. The paper is called Direct Atomic Layer Processing of Titanium Oxide Resistive RAM Gas Sensor for Real-Time Gas Perception. So if you have a chance to visit San Francisco, make sure you visit the ATLANT booth at IDM. Make sure you visit ATLANT booth also here. So what we have made in this work is what I've shown before. We took the different sensors of different thickness, measured different currents coming from this simple array, and then the Taiwanese partners, they used their existing resistive RAM chip as a second layer neural network for the classification. Unfortunately, IDM policy is very strict on not sharing any results before the conference, so I can only share this as a teaser for now. But let me just summarize, because the time is short, and share the vision. So today I try to show you how we can hard code the sensitivity of each sensor using hardware, and especially DALP. The case I presented was hydrogen sensor, but what I really want for you to take as a message is that this is just the beginning, because this approach, once we prove it can work, and I think we will prove at IDM that this approach will work for any kind of sensor based on different oxides. So using DALP, you cannot just rapidly prototype different ALD devices. You can combine different devices of different oxides of different thickness on the same wafer into the same neural network and get something out of it which is much more than the sum of the parts. And I think that's the key takeaway message. And it would not just work with gas sensors. We already have work on UV sensors, not with DALP yet, but in my lab with radiation sensors. And I have this vision of creating a lab where we have DALP and maskless lithography side by side. We have a software framework which can combine these different data into these neural networks, and any interested nerd like us here can come and deposit something new, just using the data set of different devices as Lego bricks and build something new. So I think that's the main message. Thank you very much. I hope I was not clear.